Okay, well, it looks like we have a nice quorum here. So first of all, welcome to our webinar, Sediment Characterization and Monitoring the Modern Age, the cool tools. First of all, we just want to say we really appreciate your time and spend this next hour or so with us. Just as a note, this is being recorded. I think there was a notice that came up when you first logged on, so just be aware of that. So we have some great speakers today. Craig Jones is a principal ocean and environmental engineer at Integral. He specializes in hydrodynamics, waves, and sediment and contaminant transport. He also likes to chase waves in the Pacific as long as the water is not too cold. Key fact. Grace Chang is a technical director here. She is an expert in hydrodynamics, sediment transport, and particle dynamics. And if there's an LA sports team, she's a fan, but her favorite football team is the Minnesota Vikings. I'm Stephen Benson. I'm an environmental engineer at Integral, working on assessing contaminated sites, evaluating remedial actions, and designing and implementing solutions at various sediment sites nationwide. And today I'm representing the Atlantic side of the country. So for today, we're going to discuss what challenges are commonly present in sediment sites, the impacts they can have on our sites, and then we're going to share some tools that have helped us manage these contaminated sediment sites and understand what is happening underneath the water surface. These tools have helped us reduce uncertainty at a site in order to determine and design the best remedial action, and also to identify whether those remedial actions were effective or not. We'll go through 3 specific tools: SedFlume, which quantifies erosion rate and critical shear stress; our sediment profile imaging camera, which captures images on the benthic environment, allowing us to see what is happening in the biologically active zone; and our optic system, which can monitor water quality over extended periods of time. Craig and Grace will present a bit about each of these tools, share how they can benefit a sediment site, and share some case studies with you. After their presentation, we'll have a Q&A panel discussion. We would love to hear from you and discuss any comments and questions that you may have. We'll open it up to questions at the end of the presentation, and we can call on you you can raise your hand. But if you do have anything that you want to note during the presentation, please enter in the chat function and we can revisit it at the end of the discussion. Greg.
All right, thanks, Stefan. And hello, everyone, and thanks for joining us this afternoon. We're looking forward to a great discussion, and definitely we've allotted plenty of time at the end to chat with all of you. So definitely want to hear all of your thoughts, comments, questions on what you see here. And as Stefan mentioned, please, as you go along, if you see a slide that has something of interest, go ahead and enter the question in chat right there, so you don't have to remember it after some time. I'm going to start off real quick, actually, the description of this picture. This was a few winters back in Santa Cruz, California, where I am, and this is the Pacific Ocean on the right-hand side, as you can imagine, and a roadway crossing nearby a lagoon, where a roadway has been built across the mouth of a lagoon. Typically, there's about 150-yard sand beach in front of this. And during the winter, a lot of that does get eroded away. However, during this very large storm event, the beach was completely gone. A large wave event hit during a high tide. And as you can see here, water is starting to cross the roadway. Well, some of these blocks, some weighing as much as a ton, were washed up and over the roadway during the peak of the swell. So we're facing a lot of issues that deal with sediment nationwide and worldwide, that go from everything from coastal resilience to a lot of the contaminated sites that many of us are looking at. But beneficial reuse of sediment is something that's been a big topic lately as well, and how we can use sediments beneficially to help protect and make us more resilient to climate changes or moving forward in the future is very important. So why do we care about sediment? This is a picture of the Seattle area, and here in the lower portion is the lower Duwamish waterway, which drains out to Puget Sound. As many of you are aware, it's a Superfund site. Industrialization post-World War II released a number of different contaminants into the waterway, and now cleanup, and that is currently in the initial stages of design and implementation. But if we think about it from a larger standpoint, our ports and harbors are also much of the economic engine of the United States as well. So we have incredible economic benefits that these waterways provide as well, and are important for economic security. So when we are dredging, that is an important component of that economic viability for ports and harbors. As I mentioned, climate change is a challenge for many of these areas as well. And then, of course, there's many social benefits that are derived too, with people with large populations living near water in the United States. How we handle and manage that sediment is critically important to all of those sustainable uses of any waterway. So that's why we care about sediment. Sediment is a critically important component of anything that we're dealing with in, around the water, and frankly, even in upland areas in the United States, because there's a lot of opportunities for beneficial reuse of sediment. But quantification of these transport processes is necessary for any sustainable site management. So that's really our motivation here today, and talking about the tools that we can use to look at some of these different processes. So we're going to focus today a lot on contaminated sediment. And with that, I'm going to start us off with our management questions, because anything that motivates us as far as where we're going is going to be management oriented. And how do we deal with the sediment? How do we characterize it? What are we doing with it? So the ones that I'm focusing on today and that we'll be talking about a lot are from the User's Guide for Assessing Sediment Transport at Navy Facilities. And we worked with the Navy and a team of experts to develop these questions that are consistent with Army Corps of Engineers and EPA principles for looking at sediment at sites. One of the first ones is, could erosion of the sediment bed lead to exposure of buried contamination? So certainly when we're looking at a site like the Duwamish, sediment erosion and exposure to historic contamination is a critical question. And then, will sediment transport lead to redistribution of any contamination within the site or movement of contamination off-site? So big events, tidal processes, I showed the big wave event in Santa Cruz. Could that move contamination around to possibly pose further ecosystem or human health risks? And then, will natural processes lead to the burial and isolation of contamination by relatively clean sediment? So that's recovery. We talk a lot about recovery at sites, and clean sediment coming in naturally, or even enhanced natural recovery, where we can bring in clean sediment to help cap or protect contaminated sediment, is a critical thing that we're looking at many of these sites. And then finally, if there is active remediation at a site via removal or capping or other sequestration methods, could sediment transport lead to recontamination of the site? So could other sources, far field or near field, recontaminate remediation that's being conducted? So that's going to be a lot of the lens that we're looking at today. I'm going to start off with the sediment bed and looking at what's happening in the sediment bed, and then Grace is going to look more into the water column. The sediment bed, if we're going to start at the bottom where things start often in these systems and where contaminants are often concentrated, the sediments in a system are complex. Natural systems have significant changes in morphology. When we talk about morphology, this is the lower Passaic River, which is a tidal river in the Newark area, which does have bidirectional tides. The upstream direction is over here to the left side of the figure, downstream is right side. But we end up with broad shoals on the inner bends of the river, like we see on any typical river. These are also intertidal, so they will dry out to some extent during low tides and wet and flood again during higher tides. We have deeper channels that are maintained, typically on the outer edges of the river where sediment doesn't accumulate as much. And then we have anthropogenic features like bridge abutments, where there may be scour around these abutments that are maintained due to the flow past these abutments. But all of these are essentially different sedimentary environments that we need to look at. And they also change over time. So we can get a big storm that can mix up things quite a bit, but how much? We say quite a bit, or it could happen, but we really need to quantify those answers so that we can address our management questions in a good way. So a lot of the tools that we're talking about today are meant to address these questions. So I'm going to start off simply with a conceptual site model. And what is a conceptual site model? We hear that term all the time, but essentially in sediments, it's an initial assessment of sediment transport patterns based on available information. So it's when we go in, we just looked at that map. I talked about a few of the things that are happening. That's an initial conceptual model of that bend in the river. Deposition on inside bends, not deposition on outside bends, potentially scour, or just the dynamic stability there. But it's put a few terms out here as well. We're going to talk about erosion or erosion flux, and a flux is just an amount of mass moving in a certain direction. But erosion is when the currents in the system, or the bottom shear stress, which is the force generated across the bottom, is high enough to move sediment away from the sediment bed. It then becomes suspended and moves around in the water column, and Grace is going to talk a lot about that. And then it hits an area where the flow is slowed down and the sediment can deposit out. Now, this can happen at one location due to tides that are lifting sediment up, eroding sediment up, and depositing it back down. But generally in an area over the long term, it will tend to be erosional, depositional, or fairly stable. So those are the kind of things we're looking at characterizing. One of the things we can do right away is start to apply some rules of thumb. Coarser grained areas, sandy areas are typically high energy environments. That's why beaches are sand, because the waves are acting on it all the time. Waves are a lot of energy. It keeps any mud or silt or fine sediment from depositing. Contamination gradients also can give us a lot of insight into directions of transport as well. High concentrations will tend to be near sources or into highly depositional areas. And then those contamination gradients will decrease as we move in a downstream direction, or if we're in an area where there's no sediment accumulation, we may not see any contamination. One quick example is here. I'm going to talk a lot more about sediment profile imagery in a bit, but here is some sediment profile imagery in that same bend in the Passaic River. So we talked about that inside bend, lower energy. Well, here's a picture of what the sediment looks like. It's a lot of leaf and fine silt all mixed up. And if you think about organic material like leaves, that is not heavy stuff that stays down the sediment. It's only going to deposit out in a low energy area. Whereas if we start looking on this bend out here, on this outside bend of the river, we don't see any of that leafy material. We're talking 100 yards away here. This is much more consolidated, stiff silt and clay that is very difficult to erode. So this part of the river is essentially scoured down to the stable sediment bed here. So when we're talking about erosion, what can we do to look at that? And there's a device called Flume. There's actually, we're calling it a cool tool because it's a really excellent way to get at sediment erosion. It was actually developed in the 90s at UC Santa Barbara by Willie Lick and Joe McNeil. But one of the things that we can start to do here, one of our problems here, is that we have many layers even in fine sediment beds. So at the top, we can have what's often termed a fluff layer of oxic sediment, low deposition that moves very easily. And then we get rapidly down into a mixed zone of more consolidated sediment, down to deeper consolidated sediment in these dark areas that are very stiff clays, if you want to think about it that way, stiff silts and clays. This all happens over 10 centimeters in the sediment bed. So it can be very challenging to quantify this. So with the Flume, what we can do is start to go core areas like this and look at the down core erosion properties. So in the Flume, a core is taken and it's inserted up into a flow channel here. Here's a further afield picture of it where that core is inserted into a flow channel. That a known shear stress can be applied. So that known current that we were looking at, that force on the sediment bed that causes erosion. And here you can see through a viewport, this is a sediment eroding. As the sediment erodes, we can move that piston up and you can see the sediment rising here so that it keeps up with the erosion. So what we can do is actually measure the velocity of erosion for any given shear stress. So now we have that complex layering in the core that goes down core that we can't really predict from properties. So this is an engineering tool to go in and directly measure those properties. So now we have a good direct engineering measure that we can start to look at to help address our management questions. So what does that data look like? Here's a core from San Francisco Bay. And here we can see there's actually a lot of worms in the top of this core. We have a few centimeters of that lighter colored oxidized sediment and layering of darker and lighter sediments as we move out. The erosion rate is plotted along here. Depth is plotted down here. So as we move down into the core, each of these lines represents an increasing shear stress. And as you expect, as you increase the flow or shear stress, you're increasing the erosion rate. As you move down the core along any of these lines, you can see the sediment getting stiffer, so it becomes harder to erode as we move down. Also, we get good data on density and particle size. Here's particle size. The red line is D50 or medium particle size. This particular core, you can see it's all silt, but there is a very down core. Some big changes, well, moderate changes in the core as we move down core. These are particle size profiles as well. So right here is about the middle of a silt. As we move, we hit a transition zone where there's a little bit of fine sand, and we move deeper to where the core becomes more and more clay, which is representative of that stiffer material. So these allow us to start to build a picture of what's happening at this location of the sediment bed. But our big question is, how do we tie that together throughout the site? So many of you are probably familiar with multibeam surveys. This is where an acoustic transducer sends out a swath of acoustic beams to essentially get a 3D map at the bottom. And that's what I showed earlier in that Passaic picture as well, and I'll show some more in a bit. But having a good 3D picture at the bottom at least lets us start to see what's happening. We can also get cores, so not only chemistry cores, but things like Flume to tell us, okay, within that survey, now we can look at some different areas and understand what that sediment looks like. But another powerful tool, final tool I'm going to talk about, is the SPY camera, where we can get imagery from the bed. Now, this approach, while seemingly logical, is something that we don't apply at many sites nationwide. We're just now getting to the point. Here's some recent work by NOAA in the offshore realm, where multi-beam surveys, some of these geophysical surveys, are combined with coring data and imagery to really integrate mapping of site sediment. These are actually looking offshore at different benthic communities offshore to help define offshore habitats. But those same techniques can certainly be applied at inland sites as well. And as a note, many of these survey techniques are getting much more cost-effective over time. And by blending with cost-effective imagery, we can start to really develop a good picture so we know where to go collect our cores that may be more intensive. So, SPY camera, sediment profile imagery, and plan view imagery. How does it work? Some of you may be familiar with it. Again, this is another technology that's not new. However, we're constantly looking for new ways to apply it to really help get better comprehensive views of sites. Here you can see this tripod, this frame, being lowered towards the sediment bed. A switch hits and it takes a plan view image, or basically just a down view image of the sediment bed. Once it hits the sediment bed, a prism lowers into the sediment. Here's a cross view section and takes essentially a side view picture of the sediment. What does that look like? Well, here's a plan view image looking down at the sediment bed at a location, and we can see critters at the top of the surface of the sediment. This one in particular has a lot of variability in it. Well, obviously, we don't see quite this many different critters in many pictures, but it's a good example. As well as we get a cross view image of the sediment where we can have that oxic layer, those lighter sediment I was showing in those earlier images, versus the anoxic or the deeper sediment. We can start to correlate those with the things that we're seeing in the sed flume. But also with the high resolution imagery we have these days, we can actually use image techniques to get grain size from the sediment. But we can see different burrows and worms, and the benthic ecologists can do an assessment with this with other benthic ecology data to look at the critters that are living at a site. One of the important things we're doing with it, under some funding from the Department of Energy, who's very interested in mapping offshore sites, we developed a system called ISpy where we can pull that imagery in and have used a lot of machine learning techniques to now automate the parameters that are collected from these images. So those parameters I was talking about earlier are now automated in this system. So number one, that helps standardize what's happening, but it also makes it a lot more rapid and cost effective to do. Here's an example of automated grain size extraction. This is my personal favorite thing. But about every square centimeter of the image, you can actually get a grain size. In this particular case, it's a pretty obvious one you can see with your eyes with pebbles over a couple of different sandy size materials. But we can start to look at the grain size throughout the image. It's not just one bulk sample we have to take to the laboratory and spend time processing it. We can actually get a lot of information just from one image. So what does it look like when we pull all this together? Here's an example from Douglas Harbor, and Gene Revelis, who also I believe is on as well, led this project for Integral, but this is up in Juneau, Alaska. Douglas Island is off here to the south. This is a tidal strait north of Douglas Island. But Douglas Harbor itself had contaminated sediment that needed to be removed, and it's still an active harbor as well. So the material was removed from the harbor, placed out into the tidal strait, and a sand cap was placed over the material in the tidal strait as well as in the harbor so that any residual contamination was not being exposed. So it was a large dredging operation, and we did spy camera at all of these locations to monitor a few different stages of the operation. Oh, here's what the images looked like. After the dredge material was disposed out in the tidal strait, here you can see that dredge material later of about 12 centimeter deep, and you can already see an oxic layer that's formed at the surface there. During the cap placement, here's an interim cap placement figure where we have 5 centimeters of that sand cap on top of the dredge material later. And then eventually, post-cap placement, we can see 11 centimeters over that sand cap as well. So they use this at Douglas Harbor as a quick verification tool of not only the depth of sand cap placement, but also the extent. And by the extent, here's a map of that sand cap, and each location shows a thickness of the sand cap. But from that, we can also construct a 3-dimensional model so we can look at what that sand cap looks like and do cross sections of it so that everyone can have confidence that a good sand cap was placed, or identify areas where there may be gaps and there might need to be placement that's back. So ideally, this integrated mapping has allowed us with techniques that we can now go in and do site screening during operations, validation after operations, and really get good baseline conditions as well. I'm going to show one more cool image that this was off the coast of Oregon at the Packwave Facility. This is a marine energy test facility where they're going to be testing wave energy devices. And we were able to do a spy survey out there in conjunction with Department of Energy, Oregon State University, and a number of other institutions. And here are all the spy camera locations. But combined with Multibeam, we were able to map out the different substrate in these areas from very coarse sands, fine sands, to even some silty regions offshore. Identify relic channels in this area that are now areas with a higher sea level stand that are no longer active. But it gives us a good baseline so that once I start installing devices out there, I can see if there's any disturbance to the benthos out there. Another site I'm going to chat about quickly is the United Hecathorn site in San Francisco Bay. So those of you familiar with San Francisco Bay, this is central San, or if you're not familiar with San Francisco Bay, this is central San Francisco Bay. The Golden Gate would be out here to our left, San Pablo Bay up to the north here. This area over to our right would be Berkeley. Oh, here's our big map here. I apologize. Richmond and then Berkeley down here, and San Francisco across the way. So this again is an old industrialized area, man-made channel in San Francisco Bay. It's a relatively short channel that's only about 1,000 meters long. There's a historic DDT manufacturing facility there that released DDT. It was dredged in 1995 under the direction of the EPA and was cleaned up. One of the challenges, though, is in 5 and 10-year reviews, the DDT levels are still very high, and a lot of that is supposed to be due to under-pier areas that were not able to be fully dredged due to debris in the area, and have subsequently come back out into the channel. So this is what it looks like. Here's our 3D image from the multi-beam I was discussing earlier. The blue is deeper with the red being shallower, so it's shallower up at the head. This is also an active shipping area right here. There's a company that uses this for mobilization out of their areas. One of the first things we want to look at is what are the processes. We have tidal exchange and we have upland sources. This is the former Superfund site here, but again, that's generally been controlled. And a large stormwater outfall at the head. So we wanted to look at what was happening in terms of our management questions. So fortunately, there are many surveys available, so we could look at changes over time. The red areas are areas that have been identified as erosional over time, and blue areas are accumulation. Over time, the volume, this YBM here is Young Bay mud. So that's essentially new San Francisco Bay mud. Over time, that's been increasing. So it is net depositional. However, we do continue to have hot spots where there is mixing and erosion. And again, a lot of that's due to vessel activity. If we go into the multi-beam and do small cross sections, you can see all these furrowed areas. And these are due to vessel scour that's moving past there. So there's a lot of vessel activity, particularly in this area, that is disturbing the surface of the sediment, even though it's net depositional. So one of the first things we worked with a company called ParTrack to do particle tracking and deployed particle tracers on the bed in the shallow areas and the deeper areas that are both fluorescing and magnetic. So we can put devices down that will capture the particles out of the water column, and by doing core grabs at the sediment bed, we can look at the fluorescence of that and determine how much is there. So the green area was one deployment location, red was another. But even after 3-4 days, we can see that the particles are distributed widely all over within the channel. So a key thing that we saw is vessel scour is a significant process at the surface of the sediment bed. So how much moves and where? We also did sed flume studies to get erosion rates of that material. That combined with some other hydrodynamic measurements allowed us to develop a model. And we can look in this particular case in the water column at the distribution of sediment that's resuspended during vessel movement activities. The good news is most of that material is limited inside the channel. There are occasional pulses moving out, but they're very low concentration relative to the local distribution. So that's one good finding from that. But that allows us to go and start to address our management questions. Could erosion of the sediment bed lead to exposure of buried contamination? Well, we did see the site is depositional. However, vessel traffic can pose an erosion risk locally. And will sediment transport lead to redistribution of contamination within the site? And we do see redistribution within the site, but limited far field redistribution. And some of that's validated by coring in that outer channel that we didn't see as much contamination out there as within the channel. And will natural porosity lead to barrow and isolation? So we do see deposition, and it's relatively clean San Francisco Bay mud. So there is a process there bringing in clean sediment that's going to help with recovery and has helped reduce the overall concentrations of contaminant over time. And if the site's actively remediated, could sediment transport lead to recontamination of the site? Well, there's still potential vessel traffic and ongoing sources. But that's going to depend on the remedies that the EPA is working with some of the PRPs on right now. So that's it for me in the sediment bed. And with that, I'm going to pass it to my colleague Grace to talk to us about the water column.
Great. Thank you, Craig, for that great introduction on sediment management best practices and for covering some great tools for characterizing bedded sediments. So now, as Craig mentioned, we'll move into the water column and we'll talk about optics, or optically based in situ characterization system. Optics is a tool that provides surface water chemical concentration data at temporal and spatial resolution that is much higher than possible with traditional discrete sampling techniques. So we'll walk through 2 case studies. One, Berries Creek study area, where we applied optics to investigate contaminated sediment transport in a system using fixed monitoring techniques, and the other, Ashtabula River, to map and characterize plumes during active environmental dredging using mobile monitoring techniques that was a collaboration between us and EPA and Battelle. So I'm fairly certain that everyone on the call is aware of the challenges involved in interpretation of discrete water samples of chemicals of concern, which I'll call COCs, due to system complexity. So this is illustrated here. This data set was generated from nearly 10 years of extensive traditional discrete sampling of contaminant concentrations at different locations throughout one of our study sites. And Craig, I'm sorry, if you can hit it again, that animation should continue. There we go, thanks. So data were collected during different seasons, different tidal phases, and different environmental conditions. So note that this y-axis is in log scale, which means that the concentrations of COCs collected in the same location span over 3 orders of magnitude. So if you squint at this figure, you might be able to say that COCs decrease with distance downstream, but otherwise it's difficult to make heads or tails out of this data set. So we could not answer fundamental site questions like, where are the COCs coming from and where are they going? And importantly, how do we best remediate the sites so that COCs stop getting into the water column and ultimately the food web? So to help answer these questions, we further developed and implemented optics, which is a tool that provides high-resolution monitoring of COC variability in the context of biophysical processes. And optics obtains data at scales that are generally unattainable through traditional discrete water column sampling. We've demonstrated optics to be effective in a wide range of environments. We've studied landlocked rivers and lakes, down to tidal estuaries and the coastal ocean for a variety of hydrophobic COCs, including PCBs, heavy metals, and pesticides. We've applied optics to many sites for remedial investigation and design and baseline monitoring, and it's been instrumental in answering many of the sediment management questions that Craig discussed earlier. Its results have informed conceptual site models and facilitated focused and effective management decisions, which would not have been possible without the high-resolution results that we obtained through optics. So what is optics and how does it work? Well, optics involves the collection of 2 different data sets, one being high-resolution in situ environmental data, as illustrated in the upper right picture, and the other being periodic co-located traditional discrete sample data, as shown in the lower right. These 2 data sets are integrated with a multi-parameter statistical regression model, and the results are robust correlations between the in situ measurements and the discrete samples of chemical concentrations. So once the model is calibrated, we can obtain continuous time series of chemical concentrations from the high-resolution data. So optics is analogous to the commonly applied derivation of total suspended solids concentrations from optical turbidity. But rather than a 1-to-1 linear regression, optics utilizes multi-parameter regression of a suite of in situ measurements against a chemical contaminant. And the result is high-resolution chemical concentration data and a better understanding of its variability in the context of system-wide environmental processes. All right, so we'll discuss 2 example optics case studies, Berries Creek Study Area, New Jersey, and Ashtabula River in Ohio. Both of these sites are affected by PCBs, and there is mercury and methylmercury present at Berries Creek. So at Berries Creek, we were wondering where and how the contaminants are moving. So the confusing discrete sample data set I showed earlier was collected at this study site. Those data were collected over nearly a decade. And due to system complexity in this tidal estuary, it was difficult to prove elements of our conceptual site model or to develop an effective remediation plan. So we implemented optics, and the result was high-resolution COC monitoring. Our goal of optics was to investigate variability of COCs in relation to physical processes in the system. We wanted to quantify the movement and, importantly, the direction of movement of COCs in the system, including transport between main channel waterways and marshes. So our optics field studies involve continuous high temporal resolution measurements from fixed platforms at main channel waterway locations, and those are shown in yellow in that map, and 3 marsh monitoring locations shown as green dots on that map. So optics instrumentation packages consisted of commercially available aquatic sensors. These sensors measure physical properties such as currents, water quality parameters, and optical properties such as fluorescence and scattering. We collected discrete water samples periodically throughout the monitoring period that covered a range of tidal conditions and precipitation events. So the optics model successfully extended our discrete sample measurements of COCs from intermittent or periodic sampling to continuous time series at 15-minute intervals. So these high-resolution results enable the examination of COC variability in the context of physical processes. So we show here time series of water level and daily precipitation in the upper row, and optics-derived total PCB concentrations in the bottom row. A dry period is on the left and a relatively wet period on the right. With optics, we obtained observations of COC resuspension during peak tidal velocities, which we highlight in purple, and deposition during slack tide, which is highlighted in green. We also measured storm flow-induced resuspension, where total PCB concentrations were observed to increase by over 3-fold. But that was followed by a relatively rapid deposition after storm passage. So optics significantly increases the temporal resolution of measurements of COCs, including during episodic events such as storms, when manual sampling is difficult because of safety concerns and frankly from knowing when a storm is going to hit. So importantly, optics helped answer our fundamental site questions. So where are COCs coming from? Well, the main channel bedded sediments. Where are they going? Into the water column and settling back to the bed during low energy periods. And how are they getting there and when? So that is resuspension during peak tidal velocities and storm events. Our remaining question was, where are these COCs ending up? So our marsh optics monitoring helped address this question. We calculated COC flux for data collected in the marshes. Now, as Craig mentioned, flux is a product of flow rate and concentration, and it provides net mass and direction of COC movement. So it enabled us to quantify the mass transport of COCs. And we could look to see directionality between main channel waterways and marshes. So the upper panel shows the flux of total BCBs calculated over a month-long monitoring period. We're showing positive flux in green, and it represents movement of material from the marsh to the main channel, or the ebb tide direction. Negative flux is shown in brown and represents movement from the main channel to the marsh, or in the flood tide direction. So here we observe COC variability with the spring neap tidal cycle, with higher fluxes during spring tide near the beginning and the end of the data series, and smaller fluxes during neap tide in the middle. We can time integrate flux over this full tidal cycle to derive net flux, which gives us information on the net mass and direction of movement of COCs over a complete tidal cycle. The results of time integration of flux are shown in the bottom 3 panels for total PCBs on the left and particulate methyl mercury and mercury in the middle and on the right. The designations NT, 8D, and WS represent the names of the 3 marshes where we conducted optics monitoring. So as you can see from these plots, at all 3 marshes and for all 3 types of COCs, the movement of materials from the main channel to the marsh, or in the flood tide direction. We can even quantify the total net mass transported over the spring neap tidal cycle. This, for example, ranged from 20 to about 300 milligrams per day for total PCBs. This type of quantitative information is not possible with intermittent discrete sampling. That's where you only get a snapshot of concentration with no information on mass transport direction. So these optics results answered our remaining question of where are COCs ending up. Our results show that the net flux of each of the COCs is from the main channel to the marsh. So our optics results were instrumental to an interim action record of decision for monitoring and adaptive management at the site, and a remedial design focused primarily on the Berries Creek main channel waterway, rather than full remediation of the marshes. And this likely saved our client hundreds of millions of dollars. And it is based on scientific evidence, not just optics, but multiple lines of evidence. And the results here are published in the peer-reviewed literature. Okay, so our second case study is the Ashtabula River case study. This was conducted in collaboration with Battelle and the EPA in 2007. In 2007, over 400,000 cubic yards of PCB contaminated sediment were dredged to remediate the Ashtabula River. This river is in northeast Ohio, and it empties into Lake Erie. Lake Erie has a seiche effect that results in water flowing in both directions, like a very high frequency tide, and it contributes complexity to this contaminated sediment site. So our primary objectives of this EPA study were to map and characterize the dredge plume and to estimate the mass of resuspended PCBs during dredge operations. Our analysis used data from several different field measurement techniques. The middle photo shows a moored current meter, which was co-located with optical turbidity meters and deployed upstream and downstream of the dredge plume, as the arrows indicated, and that's outside of the area of influence of dredging. So the moored optical and acoustic backscatter data provided high-resolution information with which to derive temporally varying background or non-dredge related solids and PCB concentrations using optics-based empirical correlations. We needed to measure the background conditions up and downstream of dredge operations because of that seiche effect that causes flow reversal at variable intensity, frequency, and duration. The photos on the right show our vessel-mounted measurement techniques that we used for spatial mapping. The upper picture is our vessel-mounted current meter. We use that to measure cross-channel, depth-resolved flow rate, and acoustic backscatter. And the data from those were combined with vessel-based optical turbidity measurements and discrete samples of total suspended solids and PCBs that were collected using that multi-depth water sampler shown in the bottom photo. That was developed and operated by our colleagues at Battelle and the EPA. So we performed two types of vessel operations. The first I'll talk about is what I'm termed progressive transecting. And these are data from paired cross-channel transects that began at predetermined distances upstream of dredge operations and progressed to set distances downstream of dredge operations, as indicated in that picture. So data from the progressive transecting were compiled and analyzed to map and characterize the dredge plume for each day of dredge operations. We first determined the background solids and PCB concentrations from the moored measurements that were made outside of the influence of the dredge operations and subtracted that from our mobile transect data to create 3D maps of the suspended solids and PCB plume. From these 3D maps, we could characterize the dredge plume, including estimating the dredge volume of suspended solids and PCBs. The second type of vessel operations was what we termed as group transecting. Group transecting involved the collection of transect data repeatedly in the same area back and forth over periods of about an hour or more. We repeated many groups of transects at predetermined distances from the dredge and used grouped transecting data to make estimates of the mass of material resuspended during dredging. So we computed flux of solids and PCBs for all transects in each group, where again, flux is the product of flow rate measured by the current meter and concentration, which we derive from optics-based empirical regressions between our discrete water samples and our in situ measurements of acoustic and optical backscatter. As we saw in Berries Creek, measurements of flux contain information about transport direction. So we could separate solids and PCB flux data that were associated with dredge operations from those due to natural conditions like river flow or that sage. So to do this, we evaluated whether the flux direction was pointing away from or toward the dredge. So if away, it was attributed to dredge operations. In other words, we have higher concentrations starting at the dredge and moving away, and that's that gradient that Craig was talking about earlier. And those data that were attributed to the dredge were retained for further analysis. If we found that fluxes were pointing towards the dredge, in other words, higher concentrations away from the dredge, it was attributed to natural processes, and we removed those data from the data set. So all dredge-related flux data in each group of transects were integrated over the time period of grouped transect collection and plotted as a function of distance from dredge. And that's that figure shown to the right. We were able to fit a power law regression to those data to estimate the mass of PCB residuals per hour of dredge operations as a function of distance from dredging. So from the sets of group transecting data, we could develop a predictive relationship of PCB concentrations as a function of distance from dredge that could be used to inform management of future environmental dredging operations, including monitoring and mitigation. So we applied systematic field measurements and optics-based regressions to provide data at spatial resolution necessary to map and characterize the solids and PCB plume associated with environmental dredging. We mapped the dredge plume in 3 dimensions, estimated its volume of solids and PCBs, and estimated the mass of resuspended material during dredge operations. So I'd like to summarize this section by showing optics performance analysis results for a storm flow event. Now, this picture on the left shows PCB and net flux determined from continuous optic sampling. It's at 15-minute resolution. So I'm going to step through some examples that compare this to net flux that is determined from intermittent discrete sampling. Now, hypothetically, if flux is computed from 2 discrete samples that are collected 3 days apart, bracketing that peak flow, then the resulting net flux computed from these 2 samples would be over 60% underestimated from flux computed from continuous sampling. Not surprisingly, there's high uncertainty with intermittent sampling, including missing the crucial information like COC mass transport during peak storm flow. So I'm going to step through a few more examples pretty quickly. These are, again, randomly selected times of discrete sampling, assuming 2 samples at daylight periods. So 2 samples collected following a storm would result in underestimation of net flux by close to 80%. If we wait 2 and 3 days following peak storm flow, the net flux is underestimated by over 90%. If we go out and collect 2 samples on the same day, we get underestimates of nearly 100%. And then if we again catch, bracketing that peak flow, we're about 50% underestimated. So we've presented a cool surface water sampling tool, optics, that can fill significant data gaps left by traditional, intermittent, or periodic surface water discrete sampling. The 2 case studies in this storm flow performance analysis demonstrate that the amount and utility of data collected using optics is much greater than with traditionally sampled data. Cost performance analysis of 4 different optic studies demonstrate that per sample cost reductions from traditional discrete sampling methods range from 85% to more than 99%, depending on COC type and monitoring duration. So thanks for your attention, and I will now turn it back to Stefan to wrap up.
Great. Thank you very much, Grace. That was really informative. So what did we learn? Well, just to sum up quickly, we shared 3 tools. We talked about SedFlume, which quantifies the erosion rate and critical shear stress. We talked about the sediment profile imaging system, which allows you to see what's going on in the upper surfaces of the sediment bed. And then Grace just discussed the optic system that captures continuous information about water quality. So these 3 tools have really allowed us to characterize the sediment bed and the water column in order to gather key information about site conditions. And using these tools either separately or in conjunction with one another has really enabled us to refine the conceptual site model and work with the client and the regulators to develop protective and cost-effective remedial actions and monitor how the water systems are responding to those actions. So now we're going to open up to the audience and see if you have any questions. At this point, we'd really love to hear from you. If you have any questions, please raise your hand using the reactions icon on top, and we can enable your mic, and you'll just have to make sure you're unmuted. So while you're looking at that, I had a question for Grace just about the systems that you're using to measure chemical concentrations with the optic system. Is that approved by the regulatory agencies, and how does that really differ from the results if you submit it to a lab for analysis?
Sure, good question, Stefan. So the optics method has undergone official EPA peer review and was accepted as part of the record of decision for Berries Creek. We've also published the results in the peer-reviewed literature for Berries Creek and also for South River, Virginia site. So it has been reviewed twice for that. And the USGS has published the results for San Francisco Bay Estuary. That is in Limnology and Oceanography by Brian Bergamaschi and colleagues. And then the second question you said was, how does it differ from discrete sampling? It uses discrete sampling for the empirical regressions against the in situ measurements. So it utilizes the data and calibrates it and validates the model with it. So in a sense, the data are the same. That error analysis that we have done to validate this model is the same as laboratory, replicates, but it extends that time series. So rather than getting periodic or intermittent samples, you can get continuous data.
Great, thank you. We have a question in the chat from Sujin. How did you correlate the optics results to PCBs, mercury, and methylmercury concentrations in water?
Sure, yep, that's the whole premise behind optics. So generally, hydrophobic contaminants will associate with particles, and particles tend to be stickier that have the contaminants associated with them. And sticky particles are generally more organic in nature and have unique optical signatures. And so we deploy optical instrumentations that can tease out those unique optical signatures. And also a lot of these materials, they move with the physical processes in the system. So their variability is dominated by physical processes that can also be measured by our aquatic sensors. So by combining the suite of optical measurements with laboratory-based measurements of these chemical contaminant concentrations, we can derive the high-frequency chemical concentrations from our in situ measurements. So like I mentioned, it's very similar to deriving TSS from turbidity. You collect your TSS samples, you measure high-resolution turbidity, you correlate them together, and you use that high-resolution data to fill in the gaps left behind by that discrete sampling.
Grace, one thing I'd add and almost ask is that originally the work that Brian Bergamaschi did in San Francisco Bay was around mercury and methylmercury, which are not, I mean, they're hydrophobic, not as hydrophobic as PCBs. So I think when we went into Berries Creek, the initial hypothesis was, well, if this works for mercury, it's going to work fantastic for PCBs. And I think, in fact, that was the finding with PCBs, right?
Yes, and for copper and lead, those regression results are extraordinary. And we're looking at R squared of 0.99. So yeah, thanks, Craig.
And Grace, how long does it take to get the results from the optic system while you have it underwater?
Well, it can be instantaneous, or it can be during set time periods that you schedule out to recover the instruments. So for the studies that I showed today, we did them as kind of a post-hoc analysis. So we let the systems collect data for, say, 2 weeks to a month. We go and retrieve the data. We wait for the laboratory results and we apply them. But we have in the past calibrated a model and then collected in situ measurements that are telemetered in real time to our desktops. So every 15 minutes, we can log on to a system and we can see data coming in and apply that model as time goes on. So something like the dredge plume mapping could be done in real time during dredge operations. Well, it's a great question. Thanks.
I got a question for you with the sediment profile imaging camera. How long does that actually take to deploy from location to location? How long does each one of those images take to collect?
So I'm gonna start on the long end. That's a good question. So if you noted on that slide, I didn't say it explicitly. It's a system that's depth rated for 4,000 meters. So recently we've done some surveys off the coast of Florida and in the Gulf of Mexico in 3,000 meters of water, so over a mile deep. The time on that is often referred to shipboard as wire time. It takes a long time to lower it to the seabed in those cases. So those surveys, station to station, can be quite a long time to safely lower the equipment to the seafloor and bring it back up. However, and those ships usually operate 24 hours a day and have multiple crews operating the equipment. However, in the shallow systems, like I showed, even off of the coast of Oregon there, which is 40 to 60 meters, that's typically on the order of 10 minutes a station to lower it to the seafloor safely, get the imagery and come back. If we're in shallower estuarine systems, even faster than that. The main constraint becomes transit time from station to station and getting on station. So it's not uncommon in an estuarine system like Puget Sound to get many dozens of images per day at stations. So compared to coring, it is a much faster method for getting around to stations and getting a lot of data.
Yeah, and then Craig, I would add too that you don't have to wait for laboratory results to get information. You get the pictures right there. But we don't have to develop film anymore either.
Mm-hmm. That's another good point, and Gene Rebelus, who heads up a lot of the SPY operations, will get daily downloads from offshore. So even when we're getting data 20, 30 miles offshore, we can get data at the end of the day emailed back to shore with a lot of the good satellite technology we have today.
I don't know if you saw that question that just popped up in the chat there. Miranda asked, do you have a small mobile SPI device that would enable its use on very remote and difficult to access waterways that might be only accessible by foot or small boat?
There is a small hand portable SPY camera that ocean imaging systems that make the SPY camera have developed. So yes, and in fact, I was involved in a project in Italy where we were in a small river and a meter or so deep and collected SPY imagery in that river throughout the river all upstream and had some exciting journeys down through rapids on a John boat with a SPY camera.
Yep, and we've applied that small system on San Francisco Bay too. I think that image with all the worms on the top, that said Flume image, we actually went out and did a SPY survey to look for those worms, and we found quite a bit of them using SPY camera. But it was a very simple technique then. We just drove around and pogo sticked until we found the worms, and then we concentrated our image collection where we saw the worms. So really neat technology.
Would that be sampling bias, Grace?
No. This is a National Science Foundation project.
So you're allowed to bias results?
Yeah, we're looking specifically for them to look at canopy flow over the sediment bed. So don't peer review my paper, please.
That actually was an interesting site in South San Francisco Bay where we did have co-located SPY imagery, SED flume coring, and then high resolution measurements in the water column of not only all the particle properties that Grace was talking about, but of the near bed hydrodynamics. So it's looking in very shallow areas at wave resuspension of sediment. But on shallow mud flats, you can imagine that the biota has a large effect. So it's not just the physical properties, but the biotic properties that vary significantly season to season that can influence the resuspension properties of the sediment. And then subsequently, in those very shallow areas, it's not just that effect on the resuspension of sediment, but the more sediment you resuspend, in those locations, you can get high enough concentration of sediment near the bed that it can also influence the shear stresses near the bed. So it was a fascinating project we did in conjunction with Stanford University, looking very carefully, that, as Grace mentioned, was funded by the National Science Foundation. So even though we're looking at a lot of really neat ways to broadly address these management questions, there still are a lot of very focused questions in sediment transport that we're actively working to address, and many of these tools are being utilized to help address those science questions.
And then Grace, with the optic system, what constituents can actually be monitored with that system itself?
Yep, so it's mostly hydrophobic chemicals. We have demonstrated it for, in addition to the PCBs, mercury, methylmercury. I mentioned copper and lead, DDT, dioxin. The one limitation we have found to date have been PAHs. I think we hypothesize it's because PAHs transform chemically in a system, and those chemical transformations are not measured by our in situ aquatic sensors. So we can't capture that variability with our measurements. But if it is PAHs that are modulated primarily by physical processes, let's say by tidal movement or storm flow, then I think we could get some pretty good results with optics.
Okay, we do have a question from Stein. You briefly showed a sediment survey map of Packwave, which I have been interested in recently. Apologies if this was answered earlier and I missed it, but is that sediment information publicly available? If so, would it have to be through a Packwave specific publication? How could I reference the data gathered from these tools?
Great question. And in fact, I'm going to go, I believe, forward into some slides we have. This was, well, apologies. This may take a moment. And I promised everyone else on this call, Stein and I did not collaborate beforehand on this. Stein and I have never met. So the Department of Energy funded us to look at applications of SPY camera for exactly these types of environmental baseline studies. And for those of you who don't have much of an interest in offshore sites, this is still just an amazing case study. So this is offshore of Oregon. Here's Newport, Oregon here. So this is central coast of Oregon. Packwave is a recently permitted offshore energy site for testing wave energy devices, as I did mention earlier. The depths are approximately 40 to 60 meters of depth, so on the order of 150 plus feet, and a lot of different types of substrate out there. The information, signed, short answer to your question is absolutely, this is publicly available. And please reach out to us via email, and we can share the reports on this study. And happy to chat with you more about it, because this was something that Gene led up and we're super excited to work on. So there were numerous box cores and SPY camera done really to see how well SPY camera could do at looking at the real world data out there. But also for its use in monitoring tools so that we can get a baseline study, and then after devices are installed, look at how things change over time. So one of the things is there's a lot of variability in the benthos out there. It's mostly sand, but you can see sand silt mix with vegetation, shell hash, and other things going on out at the site. One of the things we also get from backscatter, I'm going to dive deep for just a second here, but is backscatter. So as the acoustic energy reflects off the bottom, it has a backscatter intensity to it. So the bluer areas are softer areas that are more absorbing of the sediment. Red areas are harder areas that reflect better. As you can imagine, sands and coarser sediment reflect better, where silts and things like that absorb the acoustic energy better. So here you can see the bright areas. Those are areas I showed as coarse sand earlier, and areas that absorb a little better. So here's that map I showed earlier. So with the SPY camera data, we're able to validate the different sediment sizes out there and create a substrate map. And this CMEX is Coastal Marine Ecological Classification System developed by NOAA for classifying benthos at a site. So we're able to develop a good classification for the site. Furthermore, of interest to those of you who have an interest in the biology, so it's all mostly sandy out there. But as you can see in the plan view, there's a very different density of burrowers out there. I'm not going to attempt to pronounce the name of this particular critter that's out there. However, you can see the big difference in density of burrowers. We can actually correlate that burrow count not only to the SPY penetration depth, but what we're seeing in the SPY camera. And now we can develop heat maps of burrow densities offshore. So this is that same area. The red areas have higher burrow densities, and the green areas have lower burrow densities. And R² is a 0.8. So there's a lot of data in this SPY camera imagery alone that can be correlated to offshore conditions.
So Craig, were those results of presence of biota and density of biota, are they going to inform where devices can and cannot deploy? Or is it saying, okay, we don't want to disturb this, I'm not going to pretend to pronounce that either, this critter?
Actually, I mean, that's a great question, because benthos is extremely resilient to physical disturbance generally. I mean, that's all qualified to small scale physical disturbance. So anchoring in these areas is not anticipated to have a large effect on the benthos. However, what we're demonstrating is that tools like SPY and the multi-beam backscatter used together can provide a valuable way to validate those types of assumptions. So really that's what comes into play with an adaptive management framework, which comes into play for contaminated sites to offshore renewable energy sites, is the ability that we need to get out there with different technologies, whether it's remedial technologies or offshore renewable energy technologies. And then we have reliable tools that we can monitor and validate hypotheses we have, because we can make hypotheses, but we don't know until we get out there and can start measuring what's happening. So developing good monitoring tools is extremely important, which is why the DOE was funding this effort. So Stein, great question, and obviously you got me on a complete sidebar there.
Yeah, and it got me all excited too, because I'm thinking, wow, you know, what if we had identified some like new deep water coral habitat or something? Would that have been a, you know, no development here, or what would have happened?
True. I mean, if you see habitats that are high value and threatened habitats, and another part of it is, what role is climate change having, and being able to characterize what role climate change is having with some of these offshore habitats. Anyway, a whole long discussion.
Grace, think about the optic system. Have you seen any uses of that system for evaluating stormwater and seeing what stormwater contributions to water bodies are?
That is a very good question. We have not looked specifically at that, but we are currently funded by ESTCP to demonstrate optics at two Navy or DoD contaminated sediment sites. And our two demonstrations will be revolved around, one, stormwater flow and outfalls, and two, mobile monitoring during dredging. So if anybody out there, participants, have a site assessment need and would like for us to demonstrate out there, please do reach out. Our emails are on the screen right now, so please let us know. And that's a great lead-in question, Stefan, and that wasn't organized either.
Does anybody else have any other questions? Any parting thoughts from anybody? Okay, probably go to the next slide there, Craig. First of all, we just really like to thank everybody for taking time out of your day and participating here. We know everybody's busy and it's really valuable to us, and we hope this was valuable to you as well. So we are going to be out and about at various events coming up here. So we have the Offshore Technology Conference coming up in Texas. And if you're there, there's going to be an integral mixer on May 2nd at Kirby's Ice House. So please make sure you're going to attend that. The Chemistry Council of New Jersey on May 2nd and 3rd, Atlantic City. We'll have a booth there at the conference, so come visit us. And at the SMWG Sponsors Forum, we'll be doing a panel on environmental justice and contaminated sediments, and that's May 4th and 5th, and that's going to be a virtual event. So, gosh, those are actually becoming rarer and rarer. It's amazing. And then on May 22nd is the Big Battelle Chlorinated Conference. So that's going to happen in Palm Springs, and we'll have the booth there as well. And then also sign up for our sediment newsletter. The benthic zone, we sent that out recently. We'll have additional issues coming out. So the website is at the bottom of this page. And I think that's probably linked to on our website as well. And if it's not there, I know it's been shared on our LinkedIn page too.
And I will add, Ken, I saw you ask a summary of the presentation. We will have a recording of this available. So I think we'll follow up with a follow-up email to everyone who participated on that. But I will add, early in 2023, we'll finally, hopefully, be the Battelle Contaminated Sediment Conference. And I'm sure many of you have been following the fall starts over the past few years due to COVID and otherwise. But Grace and I and some colleagues from the Netherlands teach an all-day course on sediment transport tools and techniques, but from the baseline up, so you can walk away with a good knowledge. So we'd love to have you join us. I believe the next Battelle conference, I forget where it's going to be, in January of 2023, February of 2023. Austin, Texas, where are they? Does anyone remember? Anyway.
I haven't even seen it.
All right. Well, thank you very much for your time, everybody. Really appreciate it, and have a great afternoon.
Thanks,
Yeah,
everyone.
thank you very much, everyone.
Don't hesitate to reach out to us with any questions or comments.
Take care.
Bye-bye. Thanks.